Hello class, my name is John Davis. This is my presentation for CSC340 Digital Logic Design. We're going to be taking a look at the development and history of the RISC-V instruction set architecture. Some things we're going over include key terms and basic terminology, an introduction to other instruction sets or ISAs, a history of the development of RISC-V, what RISC-V is, and lastly, how it relates to our class in digital logic design. So when we refer to computer architecture, we typically are talking about the hardware and software specifications that make up a specific computer system. What this really means is that different computer architectures will handle certain tasks differently. This can either be a good or a bad thing, and some architectures are able to handle certain tasks more efficiently. An ISA, or instruction set architecture, is part of the abstract model of computer architecture, but it more specifically refers to how the CPU executes and handles certain tasks, such as data types, opcodes, interrupt handling, multi-thread support, and much more. Some popular ISAs in recent years include x86, ARM, PowerPC, and many more. RISC-V is an open ISA that is the fifth generation of processors built on the reduced instruction set architecture, also known as RISC. General design philosophy of RISC is to design a smaller number of instruction types so it can operate at a higher speed. RISC also has a philosophy of having the microchip do as much work as it can do without resorting to software. Additionally, RISC microprocessors are typically used in systems that perform the same task over and over again, such as printers or calculators. RISC-V began development in 2010, and its notable features include being open source, easily scalable, and affordable. After hearing all that technical jargon, it may still be confusing as to what computer architecture really is. Computer architecture is just the abstract term used to refer to the computer system as a whole. Different implementations of computer architectures are referred to by their instruction set architecture, and the ISA pretty much defines everything on the machine level. You could think of the ISA as the bridge between how the hardware components, such as the stuff that you see here like the CPU and the RAM, interact with software components. For example, what processes does the CPU use to fetch instructions from memory? As a software developer, it's important to understand how your software interacts with hardware, especially in cases where you develop multi-platform apps, which may be used across devices which do not share the same ISA. Computer enthusiasts may already be familiar with the instruction set that the CPU in their computer uses. Most desktop and laptop systems use a type of complex instruction set computing CPU called an x86 processor. x86 is considered part of the CISC or CISC computer chips. x86 was a standard developed by Intel in the late 70s, and it's found in most computers today, including workstations and servers, and even the fastest chip in the world currently uses x86. x86 is typically limited to advanced computing tasks, and less complex and/or lower power devices use a different implementation called ARM. ARM is often found in embedded systems or devices that are designed specifically to not use a lot of power for performance. Examples include smartphones, smart TVs, and other wearable consumer electronics. Generally, x86 is used in systems where configurability and expandability is expected. Additionally, x86 offers the best performance in terms of available ISAs, and you can expect a higher software compatibility due to its dominating market share. ARM offers higher system security and can be used in instances where power consumption is a concern. However, ARM chips offer less calculation capacity and is limited in its ability to do certain mathematical operations. x86 also has limitations in energy consumption, and generally the chips generate more heat. If we take a look at the examples at the top, you can see that x86 chips are typically found in devices such as workstations, gaming PCs, and desktop or laptop processors. ARM, on the other hand, can be found across a wider range of devices, such as smartphones, Raspberry Pis, and other single-board computers, and some companies like Apple have even produced ARM chips which can outperform x86 chips, but that's typically not the case. Additionally, I would say that one ISA is not inherently better than the other. There are use cases for both. The history of RISC-V actually starts with a team of UC Berkeley researchers that published a paper called The Case for a Reduced Instruction Set Computer in 1980. Alongside their paper, the team also creates the first RISC processor, called the Berkeley RISC-I. Overseas, the first ARM processor is created using RISC design ideology by Acorn Industries in Great Britain. By 1986, the first commercial RISC processor becomes available, and by the late 1980s, development of the RISC-II begins. Between the late 80s and 2005, more development is made towards the ISA, and the RISC-III and the RISC-IV are developed. However, nothing really exciting happens. Development on RISC-V begins in 2005 when another team of UC Berkeley researchers start research on a lab they called Parallel Computing Laboratory, or just PAR Lab. At around this time, the research was centered on building systems with a very large number of processor units and discussing the issues around parallelism in computer units. At around 2008, the research becomes known as Research Accelerator for Multiple Processors, also known as just RAMP, and luckily for them, Intel and Microsoft had recognized the importance of parallel computing and funded the research team $10 million. By May of 2010, development of a new chip began, and in August of that year, the RAMP project concluded. The team of researchers decided to name the new processors the RISC-V, and that was after earlier iterations of the RISC ISA. In May of 2011, the first version of the RISC-V instruction set manual is published. This document highlighted the goals of the RISC-V ISA, providing, quote, a small but complete base ISA that avoids over-architecting for a particular microarchitectural style. The ISA was designed to support 32 and 64-bit variants and also had instructions for floating point operations and multi-core implementation. In May of 2015, the RISC-V Foundation is officially founded, and in 2020 they relocated Switzerland due to U.S. trade laws. Today, the ISA has been gaining notoriety due to its open source license as well as affordability. Additionally, countries such as China has been funding development into the ISA in order to reduce reliability on foreign manufacturing. So to the right, you can see an example of a RISC-V register. In its basic form, RISC-V has 32 integer registers as well as a program counter. It uses a load and store architecture, and what that means is that the ISA divides instructions into two categories: either memory access, which load and stores between memory and registers, or ALU operations, which only occur between registers. This means that when an add operation happens, both operands and destination must be in the register. Additionally, X0 is hardwired to 0 and can either be used as a source to 0 or to discard the result of something. X1 to X31 are general purpose 32-bit registers and has a memory address space of 2 to 32 bytes. RISC-V also has fixed length 32-bit instructions that must be aligned on 32-bit boundaries. That means they must be divisible by 4. And towards the bottom, you can see the data types that are natively supported by the RISC-V C compiler. A calling convention is a set of rules on how an architecture specify how a function will be called. So in RISC-V, the calling convention passes arguments and registers when possible. And so up to 8 integer registers, A0 to A7, and up to 8 floating point registers, FA0 to FA7, are used for this purpose. Lastly, RISC-V operations do not have a means to check for a carry bit or overflow. This is due to the philosophical design of having no flags in the instruction set. In conclusion, RISC-V is an open source ISA known for its simple design as well as affordability and energy efficiency. The development of RISC-V has been driven by design principles such as simplicity, modularity, and energy efficiency. These design principles have helped set it apart from other ISAs in the industry. Unfortunately, the ISA is still relatively new, and current chips that utilize the design still fall pretty far behind both x86 and ARM chips. If you are interested in experimenting with RISC-V computing, you can go to Amazon and purchase a RISC-V chip to see what the current iteration of the ISA is capable of. Down here is one example of a more high-end computer, but you can buy SBCs as cheap as $15. So overall, RISC-V is an exciting new ISA that has potential due to its simplicity and open source license.